Good evening, everyone, or morning, or afternoon, or other times that are in the day. We are going to go ahead and wrap up. Oh, shoot. Restart. Change the scene there. Sorry. We're going to go ahead and wrap up our unit on significance testing here with one of my personal favorites. This week I collected from you some heart rate data. And we're going to be looking at that data, and we're going to be trying to make an argument to see if, or rather, we are going to do a significance test and a confidence interval to see if there is a difference in your heart rate when you're standing versus when you're sitting. This is how we do it to convince people that there is a difference. And it's also why when you go to the doctor, they always ask you to sit down when they take your heart rate. It's never standing, it's always sitting. Go ahead and mess with them next time. See if you got a good doctor or nurse and stand up. And they're going to be like, have a seat, sir. Are you kidding me? Yeah, here we go. Or ma'am. Golly, close call. Comparing means, paired data. Yeah, let's go ahead and talk about this. Now, we're going to pretend I didn't collect the data. Imagine we were sitting in the classroom. Imagine there were 30 AP Statistics students. And we wanted to do this based on what we already know how to do, and we would want to perform an experiment, giving people the two different treatments. So if we want to really argue that standing and sitting makes a difference, maybe we would randomly generate who gets what treatment, right? So the first option for us to show that there is a difference. Do humans have a different pulse when standing compared to when sitting? So the first option for us for testing this would be in a completely randomized design. We went over this way back in the day. In a completely randomized design, that is where, for an experiment, it's where you have your two treatments, sitting and standing. You're going to randomly assign the treatment to each of the two groups. So let's go ahead and set that up. How are we going to do that? What's the best method for us to do that? Well, the first thing that we do to get started is we would number the students. In this case, we only selected 13, but we would number the students or volunteers from 1 to, let's say, 13. So maybe we have 1 to 13 in our class. And since we have an odd number, I'm going to randomly select 6 of them using a random number generator, using the old RNG. Okay, then flip a coin. Flip a coin. If heads, those 6 will take their pulse. What did I say? Sitting. And if tails, the 6 will take their pulse standing. Isn't this fun? So what we're doing here is with this design, not everybody not everybody is going to be doing a comparison. And so obviously, I want you to sit and brainstorm a couple issues that we might run into with this design. So if we take a class of 13 students, we randomly select half the students to go into the sitting group, half the students to go into the standing group. Well, the reason that's a problem is you're going to get probably a lot wider variability in your samples, because maybe there's some people with higher heart rates, and maybe all those people by accident end up getting grouped into one of the groups, and it's going to kind of throw off the data a little bit. Or maybe 4 or 5 people in the room just slammed a bunch of coffee and their heart rate's already jacked up, and so maybe all those guys get put into a group, and maybe they get put into the sitting group, so the change is not as drastic as you might think. So that's kind of the issues that you can run into here. So what I did is basically I took your data and I found a couple random ways that we could do, or a couple of ways we could do a completely randomized experiment that make it kind of the results kind of inconclusive. So normally what we would do here is I would randomly select 6, the other 5. I should probably mention that. If heads, I should mention that. I should say that if heads of 6 will take their poll standing, if tails of 6 will take the sitting, if tails of 6 will take their poll standing, the remaining 5 will do what the first will receive the treatment. The first group did not. Forgot to mention that. Okay, so you have 6 are getting one treatment, 6 or 5 are getting the other treatment. It is selected randomly. And so what we're going to do is we're going to take a look at a couple of possible outcomes using our data. So here's our data. I did pull one data point out there because I think maybe they misread the directions, or someone was on my Facebook page was trolling me or something. So I apologize about that, but there was one that had a 50 heart rate increase. I think they maybe read exercise for a couple minutes and then take your pulse, would be my guess. But so I pulled that one out, and this is the data that we have. And so as you can see, there is obviously strong evidence to suggest that standing is higher. And how do we know that? Well, look at the data. Right? These numbers are generally higher. If you look at each individual person, you'll see that there's an increase for everybody. So let's go ahead and look at a couple possible samples. So here's a couple possible random generations that I ran into. What if we had randomly generated these 6 to be in the sitting group? So we flipped to heads here and we randomly selected those 6. This would be what the data looks like. Now, if we were to take the mean of these 6, and we're going to do, let's say we do the test let's say we do the inference method that we've been learning, which would be take the mean of these 6, take the mean of these 6, and then we look at, we assume that they're different, or we calculate a confidence interval. They're centered, if you look at the mean, these two groups are centered roughly around the same spot. So although the standing is a little bit higher, it's not super conclusive that there's a difference, when clearly we're looking at the data and we can see an increase. Okay, so let's look at another possible one. So these are centered at the right spot. The standing group has much higher variability, but this is a possible sample from your data. Let's look at this one. Okay, again, standing is a little bit higher, but the group they're kind of overlapping quite a bit. So it's not super, super convincing, and we could construct, or we could look through here and find data that makes it very, very convincing if we picked the right data points. But it's not probably going to be as convincing if we were to use a sample like this, or if we got a sample like this. So you're probably thinking, what's method 2? Well, one method 2 is what's called using using paired data. Okay, and basically you're saying, well, it's pretty obvious that there's a change. If you look at the data, you can see that the difference, and I'm going to specify what that difference is. That difference is standing minus sitting, okay? If we do standing minus sitting, these are the differences that we get for each individual subject. And that's where the pairing comes in. What it's talking about is you take the value from each column, you're grouping those together, and we get this nice pretty data over here. So here's the difference, and so we can clearly see that everybody had a change, everybody had an increase, and we have a mean of 9. So the average increase for each or for our group was 9 among all the people, which is pretty convincing with a standard deviation of 7. So we're saying we need a new method because getting a sample like this is not convincing. These are not convincing, and this should be convincing that there's a difference. So we use pair data. And how that works is, just a sec. Okay, we're going to use data, paired data, and we're going to use we're going to use a matched pairs design. We learned about that back in the day. We're going to use a matched paired design. Basically, we're matching each subject to the data that they took in both positions. So each student, if I can write this, each student will receive both treatments, both standing and sitting. This is what the matched pairs design looks like. Administered let me move this out of the way if you don't mind. Sorry about that. Extra time burning YouTube hours here. Administered in a random order. So what's really key here, you want to be able to say that it wasn't the order that the test was done that caused an issue. So what you can do is you can randomize. Some people take it standing first, and some people take it sitting first, because maybe most people had been sitting for a while when they started the test. So maybe that's the best technique. So it's important that you administer the treatments in a random order so that when you're done, no one can step in and say, oh, everyone sat down first. Well, that's going to cause a problem. So you have to take care of that right away. Okay, so so what we do, the kind of notation here is we're going to take all the differences and the number of differences we have, which is 11, we would call that n sub diff. So it's the number of differences. Okay, and then if we take all this data and then you sum it all up and divide by n sub diff, or you end up getting the mean, the sample mean. So we can just take the mean. Basically what we're doing, I'm just going to boil it down for you. You get all your differences, and we're just doing it like it was one single, it's like it's one variable, basically is how you treat it. So now you count x bar diff. So we find the average of this, and we're using that to estimate mu sub diff, okay? And this mu would be, in this case, it would be the average difference in heart rate for people like the ones that we're sampling in our study, the average difference you see in their pulse from between standing and sitting. Okay. And here's the distribution of that data so you can see that. And you're probably looking at that and you have some thoughts about it already. But this is the notation. So the number of differences, or the number of, you don't want to say the number of subjects, because you can use paired data on things like twins. Like there's a study where two twins are separated at birth, and they want to look at their IQ scores if one was in a low-income family and one was in a higher-income family. So they don't have to be necessarily this. N doesn't have to be the number of subjects. It's got to be kind of the number of pairs. N sub diff is the number of pairs. This is the average, and that's what we're estimating for all the people that would stand and sit. Okay, cool. Let's go ahead and move on. All right, so here's how you calculate the confidence interval. Just go ahead and take a mental image of that. This is a paired T interval here. Write that at the top. Paired T interval. That would be the method of inference that you'd be testing. Our degrees of freedom is equal to N sub diff minus 1. This is the standard deviation of all of the differences, and that's the only other thing I didn't introduce. So there's our confidence interval. There is our t-test statistic. So this is a paired t-test. Make sure I have that. Whoa. Whatever. It's right up here. This is our paired t-test. Okay, and that's pretty straightforward. Everything is going to proceed as you might think. With a paired t-test, again, where you're going to use degrees of freedom N sub diff minus 1. Your H naught is usually going to be mu sub diff is equal to 0, which means this value here will usually be 0 when you're playing it through. And then you choose, well, I think the difference is greater than 0. I think the difference is less than 0. I want to test to see if it's different at all. Okay, let's keep going. So what I'm going to do is, rather than us do a lesson on confidence intervals and a lesson on significance tests, it makes more sense, I think, to just do them both at the same time. It turns out that the conditions that you have to check for them are the same either way, so it doesn't actually matter. And it's slightly different here. So paired data come from a random sample from the population of interest, or from a randomized experiment. So that's the same. When sampling without replacement, because your condition checks, so basically your condition checks are like that of two variables in a sense, even though it's almost like we're doing a one variable test. Okay, when sampling without replacement, you need the number to be less than 10% of the population from which you are sampling, and everything else down here operates as we have done in the past. So nothing terribly new. I just changed the N1 and N2 to N diff. Let's go ahead and move. All right, so let's go ahead and do our significance test and our confidence interval. Let's do them simultaneously. So if we're going to do a confidence interval, let's just do it at 95%. So we're going to do a 95% confidence interval for mu sub diff, where mu sub diff is equal to the true mean difference. Make sure you say mean difference and not difference of means. The true mean difference, because you are taking the mean of a bunch of differences, right, for our sample, but we're trying to estimate the mean difference. And then you need to clarify standing minus sitting in beats per minute between people sitting average difference in, I should say, heart rate, and then in quotes, beats per minute, between people who sit and people who stand, or rather, I would say, between people when sitting versus standing. I like that better. Okay. That's our confidence interval. We've got our confidence level stated. We've got our parameter we're estimating stated, and we've got the kind of parameter explained in context. Okay, for a significance test, we state H naught, mu diff equals 0. Okay, HA then, let's see. All right, so I think the argument and coming into this, we're testing to see if standing makes it larger. And since we're doing standing minus sitting, we would be testing mu diff is, go ahead and take a shot at it before I write it. It is greater than 0. Okay. We're testing to see that it's greater than 0. So we're doing a one-sided test. And then I would say where mu sub diff, and great, I don't have to write it again, equals, copy and paste from over here. Okay, and then you also have to add, we plan to test at the alpha equals 0.05 significance level. Bingo. State is done. Okay, now normally you'd copy and paste that over here, but we've got everything we need to. Confidence interval, you get your confidence level, you got, and your parameter. Over here, you got your hypotheses, you got your definition of your parameter, and you've got your significance level. Moving on, let's move on to the planning stages, shall we? For the planning stages, we can actually, I'm going to come down here, and I'm going to do this. The conditions are the same. I'm going to check them both simultaneously. Okay. For the confidence interval, we are doing a paired, switch colors. We're doing a paired T interval. For a significant test, we're doing a paired T test. Bingo. Green. Sweet. Okay. All right, let's check the randomness. So one thing you need to know, the randomness check, in the survey form, we randomized the order of the form and assumed it, let's not say assumed, let's say we randomized the order of the form and participants filled out the form in the order presented to them. Now, technically, I didn't ask you to do that, but that's how we would do it if we were doing it really, really correctly. So basically, randomize the question order, and then at the top of the form say, hey, you need to report the data in the order that is presented to you. So you randomize the question order and make sure the order of the, put a little thing in here, questions on the form. Okay, randomness, 10%. In this case, we don't need to check it because we are not sampling without replacement from a larger population. We are performing a randomized experiment in the randomizing of the order of the questions. So that is just fine. The check for normality is then next. Let's go ahead and look back at the data. So we have 11, n sub diff is 11, which means if we look at the data, we see a slight issue. To me, so it turns out if you do the outliers, you do Q3 minus Q1, you get 9, and 9 times 1.5 is 13.5, and 13.5 plus 14 is, so if you're checking to see if this one outlier is 27.5, so the cutoff is just past that dot, so this actually is not an outlier, so that's okay. The problem is the data does look skewed. It looks fairly strongly skewed, and it's skewed to the right. So as of for this, for the sake of this, we would say the data, I didn't feel good about that data point, right? I would not feel good about that, but the data have no outliers. But do look slightly skewed to the right. We are not convinced that these data points, these data come from a normal population of differences. So what should we have done? Gosh dang it, guys. If all you had to do was send this form out to a couple more people, my Facebook friends are not dedicated enough. They do not love me 187 googly eyes like my wife does, who filled out the form twice, I think. So I'm just kidding. She only did it once. Anyways, yeah, so if we had 30, we'd be okay, but we don't. So actually, we have to stop here. We cannot do the test. So stop here, we're done. So on the AP exam, you would stop here. You cannot proceed with the test whatsoever. We're not on the AP exam. We're on Slagle's Mathnasium, so we can do that whatever the heck we want. But we're going to be breaking the law. So for the confidence interval, it's F sub diff plus or minus T star. And then the standard deviation of the differences divided by n sub diff. Okay, so if you want to do this on your own and try and get the interval, go ahead and go for it. I'm using this data here, so you can pause the video. I'm just going to use 9.9 and 7.12 for standard deviation and mean. Okay, so come back here. We're going to go ahead and get started. The difference, the mean of the differences is 9.9 because we took the data there. Plus or minus T star. Okay, let's think about this. T star with degrees of freedom 8. We probably should have stated our degrees of freedom at some point in here. Maybe the stage. We're going to do a significance test probably with df equals 10, right? Anyways, degrees of freedom for the test is 10. We need to find T star now for this. So basically, what we need to do is we need to find the t-critical value, and if we're doing this for a confidence interval, we need to find the t-critical value. It's 95%, so you have 2.5% in either tail for the error. I'm going to try and pull up that I'm going to pull up what you have on the test for your formula sheet so that we can take a look at that really fast. Not that one, not that one. There we go. All right, I'm going to pull up the T sheet here. So remember, since the 95% confidence interval, 5 is your kind of your error. You have 2.5% on either side. So we're looking for 2.5 on our T critical sheet. So I'm pulling up the packet. We're going to go down to the T values here. Probability, remember, just reading to the right with 10 degrees of freedom. We want 2.5% to the right. So go over. 2.5% is right there, 2.228. So that's the T critical value that you would use. If you would like to do this on your calculator, you can use inverse T here. So that's 2.228 is our T critical value, divided by our standard deviation was 7.12. And this, this is square root of n sub diff. So please change that if you did not write that up above. And this is down here is 11, square root of 11. So moving on down the pack here, plus or minus. This boils down, your margin of error is 4.78, and so with degrees of freedom 10, with DF 10, we end up with an interval from 5.126, 14.69. So basically, we're pretty sure that the mean difference in when people stand versus sit is somewhere between 5.126 and 14.69 beats per minute. Okay, so that means we should get a small p-value over here when we do our test. So let's go ahead and do our significance test. Remember, H naught is that the difference is 0. 0 is not a plausible value in our confidence interval. So we're going to do our t critical value, which is equal to x bar sub diff minus our hypothesized value for mu, which is 0, all divided by s sub diff divided by the square root of n sub diff. Whoops. Okay, and now we're going to go ahead and plug those numbers in. Well, we already know most of them. X bar sub diff is 9.9. Minus 0 is still the same. And then over here you have 7.12 divided by the root of 11. So we get a t-value of 4.615. So what does that mean? Remember, this is a one-tailed test. I like drawing a picture. So if this is our normal curve, and this is at standard deviation 0, we're looking out at standard error, I should say. We're looking out way over here for our statistic. So we want to know what that area is. So this one here, we knew the area we wanted. We wanted 2.5% in the tail, and we're finding the critical value. And then here we know so we used inverse t over here with 10 degrees of freedom. And over here what we're going to use is TCDF. So for our p-value, to find our p-value, because that's what this area represents. So that's our p-value is TCDF with lower equal to 4.615. Okay, comma, upper equal to 1,000, comma, DF equals 10. Okay, I think that's the easiest way to do it. If you want to do that on the t-table, so let's do it on our calculators first. With DF equal to 10, you get a p-value of 0.000479. Okay, let's see if we can find something similar on the table. So looking to the right of 4.615 with 10 degrees of freedom. 4.615 falls in between here, so we get, yep, something in between those two values for our p-value, both of which are less than alpha, so we're in good shape. So let's wrap up our results. They both are kind of march hand in hand. 0 is not a plausible value here, and we have a p-value less than alpha here, so both are, we have convincing evidence that the difference in heart rate when you're standing and sitting is actually larger than 0. It is a non-zero number. So let's interpret. Practice our interpretations here. We are 95% confident that the interval from 5.126, I guess we should say it like this, from 5.126 to 14 point, what was it? 69? 14.69 captures the, in context, the true mean difference. I mean, this is crucial, right? Being able to put this in context. The true mean difference, specifying standing minus sitting in heart rate, BPM, for people like the ones in this experiment true mean difference in heart rate for people like the ones in the experiment when standing versus sitting. Bingo. Significance test. What's the results? Since 0.000479 is less than alpha, which is equal to 0.05, we reject H naught. We have convincing evidence to suggest that standing increases your heart rate. Bingo. That's it. Okay. So here's the issue. You know how to do a paired t-test. You know how to do a standard 2-sample t-test. How on earth do we decide when we use what? Okay. So we use paired T procedures when we have two values of the same variable that are recorded for each individual or for each pair of similar individuals. So the one that, I always think about as an instructor, and I kind of give this in class, is like your MAP scores or your peak scores as you go through school. As you see, if we were to look at everyone's MAP scores when they're freshmen and take the average, and then take the average of all the juniors that take the exams, we should see an average that is different. That would be 2-sample T procedures. But if instead we took everybody that takes the test freshman year, and then we look at their score when they're juniors, and then we subtract the score, take the difference, and then do procedures on there, that would be paired T procedures. So sometimes in situations it makes sense. Basically, if you can use paired T procedures, you probably should. So when you have two values of the same variable recorded for each individual or pair of similar individuals, that's for situations that are like twins, or like maybe you're testing the same tree. You're a forester and you're testing the same tree, but it's in a different year. Well, it's not really the same tree because it's grown, but you see what I'm saying? So they don't have to be, exactly the same, but similar individuals. So if you have some similarity between those data, the pairs, then you should use a paired T procedure. If you don't, every other circumstance, you just use what we normally did. So this would be our parameter of interest, and you're assuming that the difference is 0, and here you're assuming that this is 0. So let's take a look at a couple examples. Before exiting the water, scuba divers remove their fins. A maker of scuba equipment advertises a new style of fin that is supposed to be faster to remove. A consumer advocacy group suspect that the time to remove the fin may be no different than the time required to remove the old fins. On average, 20 experienced scuba divers are recruited to test the new fins. Each diver flips a coin to determine which foot they wear each fin on. The time to remove each type of fin is recorded for every diver. Okay, so let's take a look at this. Should we use Pairt T procedures here, or should we not? Well, are the times, you have the time for the old fin, you have the time for the new fin. Are those two things similar in some way? Or can they be matched up and be paired? Is it the same variable? Yes, they're both time. Okay, time to remove fin. Can we take the difference? Yes, because they were both taken off by the same person. Okay, so I would say in this case we should use paired T procedures instead of two sample. Instead of taking all the times for the new fin and all the times for the old fin, paired T procedures makes more sense, because I think you're going to get more accurate results. You're going to get the results that you need. Okay. To study the health of aquatic life, scientists gathered a random sample of 60 white piranha fish from a tributary in the Amazon Reservoir during 1 year. The length of these fish will be compared to that of a random sample of 82 white piranha from the same tributary a decade ago. So this one right off the bat is a problem, because although you are sampling from the same tributary, your sample sizes are different. We can't subtract the heights. We have no way of pairing the fish from one sample to the other. So what we should do here is do two sample T procedures here. The dead giveaway is that the sample sizes are different, but that doesn't mean that it's always, so like if their sample sizes are the same, we still would have to do two sample T here, because we have no way of matching a fish from the first group to the second group. We're really talking about the river here. We're not talking about how the individual fish are changing. So that's where you use two sample. That's all I've got for you today, folks. Thanks for tuning in. It was a lot of fun. I love Pairt T procedures, and